Hi guys, Kenna here. Today we're going to go ahead and start our next unit taking a look at the properties of waves and how waves behave. And so today's notes are going to be on how light interacts with matter, and we'll start by looking at reflection. So our essential questions for today are these. What are the four fundamental interactions that light, EM radiation, because remember most of this can be applied to EM radiation as well, can have with matter? Okay. Number two, we'll introduce you to Snell's law. We'll really spend more time talking about Snell's law next class when we go ahead and start looking at refraction. But then, what is a diffuse reflection and how are real and virtual images different? This is a term that will come up a lot when we're doing our ray diagrams, both with lenses and with mirrors. And then lastly, what is the difference between concave and convex in terms of ray diagrams? Okay, so in order to do that, you have to know what concave and convex are, and we'll talk a little bit about that when we go ahead and get there. Okay, let's start by taking a look at those four fundamental interactions. Number one, when light interacts with matter, four things can happen. The light can, one, go through almost unchanged. This is what we call transparency. Two, go through but scattered. This is what we call translucency. Number three, bounce off. This is what we call a reflection. Or number four, transfer its energy to the material. This is what we call absorption. So transparent allows almost all of the light to go through, and so you can see behind the material just as if the material wasn't there, and the term we use for this is transparent. Glass is the first thing that typically comes to mind when we think of transparent, but plastics, certain types of plastics are also in this category. Air is also transparent when we see on a regular basis. And then you can see through the image through a transparent material if the surfaces are smooth like a glass window. Now, if you do not have a smooth surface, it can go ahead and start to bend some light or scatter it off into different directions, which leads us into translucent. Now, an object is translucent if some light can pass through it, but light gets scattered in different directions. Tissue paper is translucent, and so is frosted glass. If you hold a sheet of tissue paper up to the light, some light comes through the paper, but you cannot clearly see the image through to the other side. And so most of the things we think of as being transparent are not truly transparent, but in actuality are close to transparent with some amount of translucency. Okay. Then we get to the next one, which is refraction. Now, refraction is the bending of light waves. And when you deal with translucency, you actually typically will have a certain amount of refraction that's occurring with the system. But this is the bending of light waves as they enter from one medium into another. The amount of bending depends on the indices or index of refraction of the two media and is described quantitatively by Snell's law, which we will go over more next class. Refraction is responsible for image formation by lenses and by your eyeballs. Okay, so when you see, whether it's with or without glasses, you are using this refraction property. Okay, and if you do use glasses, you're using it even more to correct the position where the actual image is showing up or where the light is focusing. And then the one we're going to focus on today is reflection. Now, almost all surfaces reflect some amount of light. And remember that when we see objects, what we're seeing in most cases is the light that's reflected off those materials. The color that we see is from certain wavelengths being reflected versus others being absorbed by the material. A mirror is a good reflector, but a sheet of white paper is also a very good reflector in a different way. The difference is how they reflect, and we'll talk more about that as we take a look. The last one we introduced you to was absorption. When light is absorbed, its energy is transferred to the material. So this is actually an energy conversion like we talked about at the end of last term. When we start looking at one form of light being turned into another. We talked about this in the last unit when we were looking at things like an incandescent light bulb, right? So a lot of that energy is converted to light, but a lot more is actually converted to heat. And so that's an energy conversion. Now, absorption is also a form of energy conversion. And this is why the road surface gets hot on a sunny day. Okay, it's black, so it absorbs all of that light energy instead of reflecting it off, which causes it to heat up. A perfect absorber would look completely black because it would reflect no light at all. If you think about when we talked about color, black paper, black velvet cloth are good absorbers of light. And while we've talked about all these things very discreetly, as if, reflection, refraction, absorption, these things are all occurring in a vacuum by themselves, in reality, it is very possible for all four of these interactions of light to happen in most matter. Okay, just a matter of how much. An ordinary glass window is mostly transparent, but also absorbs about 10% of the light that's coming through it. The glass scatters some light because it's not perfect, it's got some translucency, and of course, it reflects a little bit as well. The same material also behaves differently depending on how well the surface is polished. Frosted glass has a rough surface and is translucent, but clear glass has a polished surface and is transparent. Now, you've actually experienced this before. If you've ever done any road trips and you've stopped at like a roadside bathroom, quick stop, right? If you go in, many of them don't actually have a real mirror in the bathroom. They don't want to have glass available, but they have polished metal. And so you can see your reflection in it, but it's a little fuzzy. Okay. Now, if you polished that enough, you could make it shiny to the point where it wouldn't be noticeably different from a traditional mirror. But it depends on how clean it is, how much polish it has on it to make it as reflective as possible. So the difference here depends on how the light rays are striking the material and how they're bouncing back to your eye. So let's talk a little bit about incoming and outgoing light. Incident rays are those rays that are coming in to the surface that we're examining. Now, with this particular example, you see there are three different products that can occur, or three different uh, outcomes when the light rays strike the surface. One, they can be reflected back. Okay, and as you see these rays being reflected back, you'll notice that they go in and out with the same basic angle. This is important. We'll talk a little bit more about this here in a minute. But when we go ahead and start looking at this, okay, you've got these rays. I'll just do a little triangle here. Okay, these are all reflected rays. And if you take a look at where they strike, angle in equals angle out. Angle in equals angle out. Angle in equals angle out. Okay, so those are the reflected rays. Maybe I'll color in over here so that you know that blue is going to be our reflected rays. All right. So then we get some that actually are absorbed. The material pulls them in. You see an energy conversion that's going to go ahead and turn them into something other than the typical light rays that we've been dealing with. So the ones that are dealing with here are here, here. Okay. So these light rays are absorbed by the material. And when they're absorbed, they're converted typically into heat, but they're into a different form of energy than the light that came in. And then lastly, we have those that are going to be transmitted. These are the ones that go through, but as you can see, they actually change their angle. So this is a type of refraction. So when we go ahead and start looking at these, I'll go ahead and outline these here. Okay. And this is going to be transmitted rays. But again, remember I'm saying that these, because they bend as they're going through, these are what we're going to call refracted. Okay. Refracted. Okay. Okay, so remember these ones are bent, and you can see that here, here, and here. Okay, so when we start looking at these are going to dictate how the image you see looks when your eyes perceive it. When you see your reflection in a mirror, the light has to reflect off you, hit the mirror, and then reflect off the mirror into your eye. So reflection occurs when the light wave strikes an object and then bounces back off of it. And the rule that we use is known as the law of reflection. And in the law of reflection, you have the way that light behaves. It travels in straight lines. Okay, so the angle of incidence the angle of attack that it hits the mirror with, is going to bounce back off at the same angle, which is known as the angle of reflection. And even if you change the angle of incidence, this law holds true. So once again, angle of incidence equals angle of reflection. So when you start looking at this, we can always write it out in terms of angle in equals angle out. But more accurately, what we're going to go ahead and say as we look at this is angle of incidence is going to equal the angle of reflection. Okay, so here you got here. So if we could say theta incidence equals theta reflection. And so that's what we're going to kind of keep in mind as we go ahead and go through this section, is that that's going to always hold true with respect to reflection. Once again, here it is. Incident ray is coming in. You can see the angle of incidence. Then you hit the normal. Now the normal is the perpendicular to the surface, just like when we're dealing with the normal force we talked about last term. Okay, so the normal is the perpendicular. So the angle that the incident ray comes in with respect to the normal is equal to the angle of reflection out with respect to the reflected ray. And this is where we get back to our rest stop bathroom example. Shiny, smooth surfaces, okay, perfectly flat, have a very clear reflection because all those light rays coming in at the same angle of incidence go out at the same angle of reflection. However, if you have a rough or a dull surface that is not nice and flat and polished, you end up getting what's called a diffuse reflection. Notice that the angle of incidence for all of these rays is going to be the same, but because of where it hits on the surface, they're coming off at different angles. Because again, that's based off angle of incidence, angle of reflection is based off the perpendicular or the normal to the surface at the point where it strikes. Okay, so if it was smooth, they would all come out the same way and you would get a nice clear reflection. But if it's not smooth and it's a really rough surface, those angles are going to pop out at very different directions and you're going to see very different angles as it goes ahead and pops back out. Okay, now we're going to start going over ray diagrams, and today we'll look at ray diagrams with reflection, so we're going to be using mirrors. But before we do so, it's important that we understand some basic vocabulary. There are two terms that you probably haven't dealt with like in this particular format, but we need to make sure that you understand. Those are a real image versus a virtual image. Now, a real image is made from real light rays, and I want to highlight that so that you're very clear on exactly what I mean here. Okay, so again, this is a real image is based on real light rays. Okay, so real light rays. Okay. So when the light comes in and bounces off it, the image is actually created by the coming together of actual light rays. Okay, it's said to be real because actual light rays converge. Okay, this type of image can actually be projected onto a screen. So if you think about watching a film in a movie theater, if you have a home theater set up, depending on how you do it, these are going to be real images. Now, what's tricky about this is that real images are always going to be inverted. Now, inverted means upside down. Okay, so if we have a arrow going up like this, the projected image is going to end up being projected upside down. This is compared to, say, a virtual image. This cannot be projected, no projection, and the reason for this is that the light rays do not converge. Okay, light rays do not converge. And that's why they can't go ahead and produce an image on a projecting screen. Okay, so we got to keep these in mind as we go ahead and go through here as we start looking at how the light rays move, where they land. And this is why when you're using like a focus knob on a telescope or on a microscope, you have to find that point where with your sample, the light rays converge so that you can get a crisp, clear image. If you don't, you end up with a fuzzy image. It looks blurry because the light rays are not converging. So it's an important thing to kind of keep in mind. Now, when we start looking at plane mirrors, okay, a virtual image is where it appears to be when you look into the mirror, but you know that it's not there because you're actually seeing bounced light rays that are coming off an object off the mirror. So in this particular example, you're looking at a rook from a chess set, and the eyes see it at the point where it says virtual image. Okay, I'll point this out for you right here. This is the virtual image, but the actual chess piece is not there. The actual object is over here on this side, but those light rays are bouncing off the mirror and into your eye, which makes them appear like they're actually here. But because the light rays don't actually come to these points, it is not a real image, but a virtual image. Okay, the light rays are coming at your eye as if they were coming from behind the mirror, which is not possible. Okay. All right. So this is important to keep in mind when we start thinking about these images. Now, if you look at yourself in the mirror, you get what's called left-right reversal. Okay. You think about like an ambulance. It says the word ambulance on it, but it has it written in a backwards way so that when you see it in your mirrors, it looks correct, so it's easier to read. When you wave at yourself in a mirror, you wave with your right hand, it looks like the person in the mirror is waving with their left hand because of this left-right reversal. And there are several different types of mirrors, and how they project an image or how they show an image is going to vary a little bit. We're used to using the one in the bathroom, and the one in your bathroom is probably what they call a plane mirror. It's perfectly flat. Most people don't want to have some sort of circus mirror inside their bathroom. But we have what's called a concave mirror, which is curved inward, and a convex mirror, which is curved outward. Now, I want to go ahead and make sure you're familiar with these two terms because we'll use them when we get to lenses as well. When we go ahead and start taking a look at it, if the mirror is shaped like this, so it curves like this, you can walk into a cave. So this is concave versus convex is going to bow out towards you. Convex. So the way again I remember it is that if this is our surface, as we were walking or approaching it, convex is going to come towards you, but you can actually walk into a cave. So concave is when it goes this way. All right. Images in a mirror that cannot be projected are considered virtual images. So this is a term that's going to keep coming up. So make sure that you're clear and you understand concave, convex, real, and virtual. So convex again means bulging outward or curving out. This is most commonly used to refer to lenses or mirrors which exhibit this trait, but there are mirrors as well. This would be a great place for you to go ahead and use the demo that I have posted for you with using a spoon. Okay, so take some time, kind of explore through when you're looking at how reflection or refraction works. Um, when you think about a real or a virtual image and whether it's inverted or it's not inverted, you can do a lot of this with a nice polished spoon. So if you have one, go ahead, take a minute, go get one from the kitchen. The nicer, shinier, the better. And then go ahead and try that demo before coming back and finishing up here. Okay. So again, convex means bulging outward, and concave means bulging inward. All right, let's go ahead and do this right above the words right here. So convex, if you're approaching it from this direction, this is convex because it's coming towards you. And this is concave if you're approaching it from this direction, because again, cave you can walk into. Now it's interesting if you have one of these types of lenses or mirrors, the other side would be the opposite. So if this side is convex, okay, convex, then that means the other side would be concave. Okay, and this is what you're going to see when you go ahead and play with the spoon. The pictures down below are actually for lenses, and so you can see they have what's convex lenses that are what is it called? Where you have a double convex or a double concave, or you can have what's called a planar convex or a planar concave where it's flat on one side and then concave or convex on the opposite side. But we'll deal with that a little bit more when we go ahead and get into um, dealing with the lenses. Okay. All right. Now, where do we use these? Convex mirror is curved outward, enlarges the image. Examples are rear view mirrors, store security. A concave mirror is one that curves inward and reduces the image. Telescopes, spotlights, satellite dishes, these are all examples of things shaped like that. Now, a concave mirror will make you look taller. Convex mirror will make you look shorter. A wavy mirror distorts your image so that it looks taller in some sections and shorter in others, like you can see in this example off to the right. Okay, so funhouse mirrors are using what we understand about how reflection works in concave and convex to go ahead and produce these distorted images. All right, so at this point in time, we really want to go ahead and start thinking about how to do ray diagrams. And I'll use another video to go ahead and show this very specifically. But using a ray parallel to the principal axis and one incident upon the center of the mirror, the position can be constructed by back tracing the rays. Okay, because remember, the light doesn't actually go through the mirror, it bounces off. So we can back trace to go ahead and produce this. And we use some key terms here. All right. Now, O is the distance to the object. Okay. So O equals distance to object. And sometimes you'll see them use the term D sub O for distance to object. The F is the focal point, and the I is the distance to image. And again, here, sometimes you'll see them use the term D sub I for this. Now, there's another term that I want to introduce you as well. It's not used in this example, but there are definitely times when they do that, and that's the term C. And C means the center of the curvature. So if we're dealing with a curved mirror, whether it's concave or convex, C is going to be the distance from the midpoint of, if you completed the circle, to the actual circle that it creates. And the reason that this is valuable is that the distance from center, this is an M, from center to mirror. Okay, and when I say center, remember this is referring to C, is equal to the radius. Okay. There's another valuable relationship here that we can go ahead and work on, and that's F, or the focal point. So F, or the focal point, is equal to 1/2 C. So the focal point is half the radius, okay, equals 1/2 radius. And so if they don't give you, for your particular mirror, the actual focal point, what you can then do is go ahead and use 1/2 the radius based on C. Okay, and a great lens simulator is simbucket.com /lens and mirrors / and we'll go ahead and try and link that into one of your examples so you can go ahead and play through this. But please make sure that you go through and watch the video that I create showing you how to do ray tracing diagrams, and hopefully that will help clear this up on how you can do this in terms of not only the math, but also in terms of the actual visual representation of what it is we're going to be doing. Okay, so positioning of the object with respect to the mirror is going to change how the image looks and how, whether it's a real or virtual, these types of things. Since we're using mirrors, you should know that this is going to dictate it as well. And so we want to kind of keep these things in mind as we go ahead and go through. All right. So what I showed you here is a convex mirror, okay, because you can't walk into it. But the other example we should take a look at is a concave mirror. Okay. In this case, there's a difference depending on when the actual object is outside of the focal length or inside of the focal length. Okay. And so it's important to kind of keep those things straight when we go ahead and start looking at the objects. Also notice that on the right example, when the object is inside the focal length, that the arrow is still upright. When we go ahead and look on the other side and we take a look at outside of the focal length, the object, the image appears to be inverted. Okay. And so again, let's keep in mind the O is distance to the object, F is the distance to the focal point, and I is the distance to the image that you're seeing. Okay, so watch the other video going over how to do your ray tracing diagrams, but otherwise that's all I've got for you guys today. Take care of yourselves, stay healthy, stay safe, and we'll see you soon. So long.